right. Good afternoon, everyone. We will start our webinar on electromigration. We are going to cover theory and simulation results, but mostly we will cover the theory so that we can understand what type of equations are being solved behind the scenes when we are using packages like Ansys, so that we have better knowledge as to what's being done. So we are Ozone Engineering. We are the Ansys Channel Partner of the Year back in 2015, 2018, and 2021. And we are the channel partner for Ansys. We're involved with the Ansys software tools. We do training, mentoring, and also consulting. So quickly jumping into electromigration, we'll talk about the introduction and the background. So what is electromigration? Electromigration is a physical phenomenon of mass transport in interconnects when the metallization is subject to stresses induced by high electrical current density. So then, what this results is in the atomic flux divergence. And this atomic flux divergence, either positive or negative number, it's either going to create void nucleation or formation of hilux. So electromigration has been a problem in the interconnect reliability for some period now. And what it is electromigration causes voids if there are more atoms flowing out of the domain than flowing in. That's what we call mass depletion. And it results in the creation of hilux when there are more atoms flowing in than flowing out. And that results in the mass accumulation. And you can see some pictures that describe that. And please note the scale here is we are looking at 10 micron level formation of a hillock here, and maybe at the upper picture is the formation of a void. So it's electromigration is primarily the study of atomic flux distribution, but there are more components to it. It's most significant in applications where current densities are high. And why is it that current densities are high? As you know, in electronics, everything is becoming smaller, and as the physical size of the components are becoming smaller, what's happening is the current in the smaller size is still the same, and hence current divided by the cross-sectional area, the current density is going to get really high. So the term electromigration was coined by Professor Huntington because he didn't like the German use of the word electrotransport, and so that was back in 1950s. So the term electromigration stuck in the industry. So there are two main forces that affect the ionized atoms in a conductor. First one is electric field induced direct electrostatic force, F sub E, and the force due to momentum exchange with other charge carriers, F sub P. For metallic conductors, F sub P is caused by the electron wind, and F sub P acts in a direction toward the flow of charge carriers, meaning that F sub P is in a direction opposite to that of the electric field. So the net force on an ion in the electric field is F sub E minus F sub P. And here, please note that in this diagram, the current is going from left to right, whereas F sub P is going in the opposite direction, just like the previous slide said, and F sub E is going along with the current direction. So over time, this electron wind force moves a significant number of atoms far enough from their original positions that a gap can develop in the metal, thereby preventing the flow of electricity. So the atomic flux divergence is defined by the number of atoms flowing into a region per unit time is not equal to the number flowing out of that region per unit time. So, the number of atoms flowing into a region per unit time, when it's not equal to the number of atoms flowing out of that region, then we have a what we call flux divergence. And if that flux divergence is a positive number, that means there are more atoms flowing out than flowing in. That's a mass depletion, and depletion meaning that there's going to be void formations. And when that's a negative number, that means there are more atoms flowing in than flowing out, then that's going to result in mass accumulation. So, and we have seen pictures of that. So the concentration of high current and high temperature cause the formation of these voids. The void propagates across the entire solder interface and leads to a connection failure. There are four different physics that we need to capture here. First one, what we call electromigration. The second one is thermomigration, because electromigration is going to cause temperature rise. And the third one is stress migration. When the temperatures are high, then that's going to cause stresses in the structure. And also we need to account for atomic concentration gradient. So there are these four things that we need to account for. But the traditional electromigration models are based on the solution of diffusion equations. Just the diffusion equation. It doesn't take into account all these four forces that are listed here, which is, again, electron wind force, stress gradient induced driving force, temperature gradient induced driving force, and the atomic concentration gradient. But what we are going to do is we are going to address both of these. First, we will start with the traditional electromigration model, which is based on convection diffusion equation, which takes this form here. So the traditional electromigration equation looks like this. And in this equation, capital C is the atomic concentration, capital D is diffusivity, and alpha is the reduced electromigration force. And alpha, we are going to get more into this because in the calculation of alpha, that's going to be an important calculation where we have to take into account the different physics. But staying with the traditional equation, alpha is force divided by K, which is K is this Boltzmann constant, and capital T is the temperature. And the force F in the numerator can be rewritten as Z star, which is the effective charge, multiplied by the electronic charge, multiplied by resistivity, multiplied by the current density. So as you can see from here, alpha is directly related to current density. And as current density goes up, alpha goes up. So in the traditional electromigration equation, again, listing it here, the question is, can this equation be solved in Ansys? And when I say Ansys, I'm talking about Ansys Mechanical at this point in time. Can we solve this equation in Ansys Mechanical? And the answer is yes. And here I'd like to explain how you can make use of Ansys to solve this traditional electromigration equation. So in Ansys, the first law of thermodynamics states that the thermal energy is conserved, and here in finite element formulation, this is of a transient temperature fields are calculated in finite element formulation. So if we apply that to a differential control volume, then the equation is opened up, and it looks like this, the bottom equation. And in this equation, as you can see here, it's a three-dimensional equation. That means we can solve the problem in 3D. So we can actually solve the traditional electromigration equation in 3 dimensions, which, Ansys is a 3D code, so you can do it in 3D, or you can do it in 2D, or you can also do it in 1D. So in this equation, rho is density, C is specific heat, capital T is temperature, lowercase t is time. So electromigration is definitely a transient phenomena. You create voids over time, or you create hillocks over time. So that's why we have to do a transient problem. So, so if we apply Fourier's law to thermal gradients, then we are going to get this additional equation in there. And if we add the first law of thermodynamics to Fourier's law, then we are going to end up with this equation at the top. Now, if we expand the terms, then as you'll see here, you'll get the three-dimensional representation over here. And if you'd like to reduce it to one dimension, then you can set nu y, nu z, ky, kz to 0. Then you're going to get the equation in just one dimension. So if we rearrange the terms there from time transient thermal simulation in Ansys and compare it to the traditional electromigration equation, as you can see here, those equations look very much alike. So then you can say, okay, capital D in the traditional electromigration equation is K sub x, which is thermal conductivity in the x direction, divided by rho C, the density times specific heat, and alpha, the electron force, is nu sub x times density times specific heat divided by K sub x, which is thermal conductivity. So, excuse me. So now we can also define a non-dimensional Pecklin number. And the Pecklin number is defined by this equation here. Again, it's non-dimensional. And in that equation, nu is the magnitude of the velocity vector. And L, capital L, is the element length along the velocity vector. So if we are solving in 1D and interested in just one dimensions, how the current flows from, say, left to right, excuse me, capital L is the element length. And we can also modify this for orthotropic materials, but at this point, we'll just let it go. We'll just look into one-dimensional solution. So as you can see from this formulation, alpha, the electromigration force, can now be represented as a functional Pecklin number. And as you can see here, alpha becomes 2 times the Pecklin number divided by the current conducting length. So they are very much interrelated. And in Ansys Mechanical, for the time transient solution to be valid, the Pecklin number needs to be less than 1. Otherwise, it creates unstable solutions. And just for as an example, if we set Pecklin number to 0.1, then L times alpha becomes 0.2. Now, why are we doing this? Because we'd like to come up with a normalized time and solve this equation by a finite element formulation in Ansys. So we have a one-day electromigration class, and one of the first workshop we go through is really going through this equation, and we are trying to prove that Ansys can be used to solve this electromigration equation, and this electromigration equation was solved back in 1990s in reference 1, where they produced the results that you see here, where the x-axis is basically normalized time, and the y-axis is concentration, the atomic concentration. So the challenge here is, can we reproduce these curves using Ansys? So the answer is yes, it can be done, and these are the boundary conditions you can use in Ansys. You can create a one-dimensional model or two-dimensional model, and using these boundary conditions, you can reproduce the same results that were given in a paper back in 1990s. And as you see here, the results are exactly the same for the solution of traditional electromigration equation. On the left-hand side, we are looking at results obtained from running a transient simulation in Ansys. And on the right-hand side are the results that were published in papers published in a paper, and the results were presented in that paper in 1990s. So, and we also explain how this can be done. This is the input file that's used in Ansys Mechanical to solve the same exact problem. And from here, you can reproduce the same results again. So in our class, basically, we go through this. We explain every single thing in the Ansys input file. So that way we covered the traditional electromigration equation, and and you can use Ansys to solve the traditional electromigration equation. Now, how about the advanced electromigration modeling? So please note that this convection diffusion equation is the traditional equation. However, it is not the full result. It doesn't give you the full result for what we call the advanced electromigration simulation, because we need to take into account these additional driving forces. These additional driving forces are just are these four forces: electrical field force, thermal gradient force, stress gradient force, and atomic concentration gradient. And to be able to account for these, what we have to do is look at this electromigration equation, and the Q vector here, which is the normalized atomic flux, we need to divide it up and take into account Q sub E, which is the forces due to electrical field, Q sub T, which is the thermal gradient forces, Q sub S, which is the stress gradient forces, and Q sub C, which is the atomic concentration gradient. So if we take a look at that, again, Q sub E plus Q sub T plus Q sub S plus Q sub C, and open these up. So for example, Q sub E, that's the additional driving force due to electrical field. It can be expressed in this equation here. The thermal gradient is expressed in this equation here, stress gradient in this equation here, and the atomic concentration gradient expressed here. So let's see. So we need to add all of these to each other. And we note that all these equations have some terms that are common. And we note that, it's basically this capital D, which is denoted as D sub 0 exponential function E sub A divided by K sub T. So that's the diffusivity, with D0 being the thermally activated diffusion coefficient. And we know what the Stefan-Boltzmann constant is. That's a constant, as the name implies. But we get the absolute temperature and activation energy. And it's really easy to get the temperature, excuse me, from the finite element model. So again, we look at the force due to the electrical field, and that has a Z star, which is the effective charge, and the electric charge, that's a constant as given here. The resistivity can also be expressed in this formulation, and then the current density vector is also given here. And the thermal gradient terms looks like this. So electromigration-induced void formation results in localized increased current density, resulting in these what we call current crowding. And Joule heating is proportional to the square of the current. So all of this can be accounted for in these equations, and these thermal gradients will also result in stress gradients, where we look into the local hydrostatic stress components. And if we take into account finally the atomic concentration gradient, which we have looked at before, and add them all to each other, then we are going to get this complicated expression, the Q vector, which contains all the stress gradient, the thermal gradient, atomic concentration, and the electron force. So it looks complicated, but it's all doable. It's just that we need to keep track of all these different parameters here, which are basically Ansys inputs. And if we get it all together, then we can reduce this down to this equation here. So as you see here, the Z star is the electron force, Q star is the thermal force, omega is the stress force, and C is the atomic concentration. So now this is the what I call the advanced electromigration equation, and you can still use Ansys to solve this advanced formulation. And to do this, there are really three steps. The first step is to do a coupled electric thermal finite element analysis. And the second step is to do a thermal stress finite element analysis. And then the third step is correction for atomic concentration calculation. So in the first step, you're actually taking into account the current density and the temperature gradients. And then in the second step, due to the higher temperatures, you're taking into account the stress gradients created in the structure. And then finally, you're adding for the atomic concentration. So you can use Ansys in this sequential manner to extract and add each of the advanced electromigration calculations. Again, first step, coupled electric thermal analysis, then stress analysis, and then you extract the alphas, which are really the driving forces due to current density, due to thermal, due to stress, and to that you add the atomic concentration calculation, then you come up with the final calculation. So in Ansys Mechanical, you can actually use solid 226 element. Solid 226 element, as you see, it has multiple degrees of freedom, structural, temperature, volt, current density, and concentration. So you can use solid 226 elements in 3D. In addition to that, this solid 226 element has a lot of different material models in case you would like to add more complexity, and you can add a lot of this nonlinearities to the problem, like material nonlinearities. And in terms of physics, the solid 226 element is really very versatile. It covers anything that you see in this, anything from thermal electric to structural magnetic to thermal diffusion, electric diffusion. So you can actually just use a subset of these, or you can use the full formulation like shown here, which is structural thermal electric diffusion. So this is the most advanced electromigration modeling here, and this solid 226 element has it in there. So so which Ansys tools can be used for electromigration modeling? Just like you have seen here, Ansys Mechanical Enterprise can be used. In Ansys Mechanical Enterprise is where you can use the solid 226 element for this. And we have an additional what we call EBU, Electronics Business Unit tool, Ansys SI Wave. You can also use SI Wave. So let me briefly talk about SI Wave. So we are going to switch gears, go from Ansys Mechanical to SI Wave. In SI Wave, there is what we call Black's formulation. So Black developed a model to estimate the median time to failure of a conductor due to electromigration. He published the model in a paper written in 1969, and this is his formulation primarily. This is mean time to failure in hours. This is as you see, electromigration calculation due to current density. This is not taking into account all the temperature and stress gradients. It's just taking into account the current density, but it's a lot quicker simulation. So if you have a complicated PCB design like the one that you're seeing here, all you have to do is in SI Wave, you specify the experimental constants, activation energy, and SI Wave is going to give you nice looking plots, contour plots, where on the left-hand side, your SI Wave is going to tell you what's the mean time to failure. On your complicated PCB design, you will be able to see, for example, in this case here, 2,590 hours. After 2,590 hours, you can expect electromigration failure in these red zones here. So you will be able to plot mean time to failure in SI Wave along with other plots like the one that you see on the right-hand side, the current density. And you can see that current density is really high at the same location where we are seeing mean time to failures of really hours of the order of 2,000. So in conclusion, Ansys software tools can be successfully used to model electromigration. You can either use Ansys Mechanical or for a quick calculation, you can use Ansys SI Wave. And the engineers can redesign under the guidance of simulation results from Ansys to avoid any failures due to electromigration, and so that we can address what reference 5 said as the electromigration has been the most persistent threat to interconnect reliability. So Ansys made it easy so that we can do through quick calculations to be able to predict electromigration failures. So here are the references that we were talking about in this presentation here. And if you'd like to know more, please sign up for our class. We have a one-day class on electromigration. So there are lots of different Ansys software tools as well that we look into and we provide support. In Ozone offices, we have multiple offices on the West Coast as well as the East Coast. We also are in Canada. And so here's our contact information. Please, if you'd like to get more information, you can send an email to info@ozoninc.com. If you're interested in Ansys software tools, you can send us an email at sales@ozoninc.com. If you're already our client and like to get some support, just send it to support@ozoninc.com. Our website is www.ozoninc.com, and here are our office locations. So with that, I'd like to say thank you, and thank you for your attention. if you have any questions, please feel free to ask at this point.